Good evening. Hope you're well fed and well caffeinated and well alcoholed.
Who's drunk?
Uh, okay, I am. I had some gin earlier. Okay, as you're getting settled in, we'll get begun in a couple of minutes. Quick check. I hope you can read the text at the back. If not, you're welcome to sit up front. Okay, good. Um, Closed network. Sorry, I'm not able to bridge it to the 44 con Wi-Fi. So for these couple of hours, let's suffer without internet access. If that's comfortable with you? Either of the two SSIDs, Exploit Lab 2.4 or Exploit Lab 5. Password is make security great again. I'm just going to put up a class web server for the workshop. When you get connected, the IP address is 10.50.1.185. You pop up the home page, you should see a tools icon or a tools link, except there are no tools, but there's just the slides. So download the PDF of the slides. And as you're also getting settled in, once you're connected to the network, I'll let you know what we need to do to access the targets. These are two little Raspberry Pis sitting in the corner that will be running the lab of us for us. Please don't kick that power strip because it's a little finicky. I'm already overloading it and running the risk of fire. So we don't want the router to go off. Fire is okay, but we don't want the router to go off. Then everything is going to die. So right, yeah, welcome, settle in, and Maria and I shall be, Azaria and I shall be taking you through this workshop on just some basics about ARM assembly and shellcode. Quick question, how many of you have written Intel assembly before? Okay, so you guys know what machine code is and what registers are and what the stack is and pointers and 32-bit and 16-bit. It's not like Java and cross-site scripting junk that otherwise gets talked about. Okay, if you were expecting that, this is totally not the workshop for it. Right. How many of you have written shellcode before? By hand, not Metasploit. Metasploit's cheating. Okay. Okay, so that's good. So we will do some, this is by no means a full-fledged shellcode workshop. The idea of this workshop is to get you started with writing assembly and writing shellcode in ARM. Quick overview of the tools, some templates and processes that we follow. We will do a simple shellcode, execve, just like drop to bin shell. Along this process, we'll learn a lot about, just the basics of ARM assembly, a little bit about the ARM way of doing things, thumb mode, ARM mode, instructions, load, store, blah, 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 blah. And then, time permitting, we will also talk about reverse shell and give you an idea of how to implement reverse shell. I would like to hand over the reverse shell to you as an exercise. Basically, by the end of this workshop, you should have enough armament to write your own reverse shell. And if you do that successfully, I will buy you a beer tomorrow. Show me, of course, that it works. Right. Okay.
I have my phone. Microphone.
Oh yeah, you have the microphone. So to introduce Azaria, how many of you read her fantastic ARM tutorials? That's her. She's
two.
Well, I think you're going to get a lot more hits on the site tonight. But yeah, she's done a fantastic job of introduction to ARM assembly and also introduction to ARM shellcode. So a lot of what we're going to talk about is also beautifully documented with animated GIFs, not just static diagrams, mind you, with animated GIFs on her website.
Yeah, you don't have to get all the, oops, so loud. You don't have to get all the concepts right now. So if you don't understand everything, that's okay. You can just read it up on the website at home. So no big deal.
Okay, let's get moving really fast. Okay, a couple of administrative things. Those of you on the, what is this side? My left and therefore your right. Though I'm directionally challenged, honestly speaking. I have no idea what that and that side is. But those of you on the right side, your Raspberry Pi is 10.50.50.4. And those of you on the left side, your Raspberry Pi is 10.50.50.3. The same image, they're basically running Raspbian, and we've loaded them up with GDB and some debugging tools and the bin tools to write assembly with. We are going to only use one login. The username and password is exploitlab. Please don't delete other people's work and play nice. This is not like a, death match. It's not deathmatch mode. So when you log in, there's a directory called workshop which contains the basic templates. Just make your own directory. Just give it whatever directory name you like, and copy the contents of the everything in workshop to that directory, and then stay within that directory. Don't go killing other people's directories. Okay. So that's just a little bit of the setup. If you've already been in our ARM Exploit Lab class in the on Monday, Tuesday, and Wednesday, please leave the room. You've already studied this. Joking, you can stay, but there's nothing new to be discussed here.
So can you just give me the password for?
Yeah, it's username password is exploit lab. No problem. Right. Okay. Okay, my name is Saumil Shah, and this is Azaria. Let's begin. Why are we talking about ARM? This is one of my favorite quotes, and this is actually my own quote, that there's an Intel on every desktop, but there's an ARM in every pocket. ARM's outnumbering Intel chips 5-1, maybe 6-1 by the time we finish this workshop. What are some of the salient features of the ARM CPU? Unlike Intel is what we call as a complex instruction set computer. ARM is a RISC CPU, which means there's very few instructions, but each instruction has several permutations to it. It's somewhat like C programming. You have very limited keywords, but you can do pretty much everything with it. So the whole philosophy of ARM is simplicity and frugality. ARM will try to save on the number of instructions, it will try to save on memory, it will try to save on read-write operations. Not my fault, not my fault. Okay. And yes. A few differences between ARM and Intel. The RISC world is very different. Pretty much our journey in InfoSec and reversing has been with Intel. At least that's how I have grown up. So we are very familiar with the wrong way of doing things because that's what we've learned from the get-go. And Intel assembly is now natural and familiar to us. ARM assembly, therefore, at first go sounds very weird. It even sounds illogical. But the more you study it, the more it will make sense up until a point that you will totally just not like looking at Intel assembly or however, especially if you start doing ROP chains on ARM, they're really cute and they're really beautiful and really elegant. And ROP chains on Intel just look absolutely ugly, just like a Picasso painting. Quick differences. ARM is what we call as a load store architecture. Short answer, what load store is? It means that you cannot perform any computation directly on memory. In Intel, you can do something like increment indirect EAX, which means EAX is used as a pointer. You dereference a pointer and increment the value of memory at that address by 1. One instruction does it all. you do call dereference EX, that is call a function pointer. You cannot do that on ARM. On ARM, if you want to do any such calculations on memory pointers, you first have to load the values into a register, do the calculations, and then store them back. So everything in ARM is load store, and there's a lot of load store going on. There's a lot of instructions available for load store as well. So there's a lot of instructions for calculations, like arithmetic and logical instructions, and there's a lot of instructions for load store. There's pretty much no other types of instructions except program control transfer, which is branching and things like that. From ARM, ARM has several evolution steps along the way. It started with ARM v1, that is the basic 32-bit computer, which was the Acorn Archimedes. That computer was way ahead of its time in the late 80s. It was the successor to the BBC Micro. So ARM v1 first came up with a 32-bit ARM instruction set. And currently we are using ARM v6, ARM v7 and ARM v8 instruction sets. Most of your phones are ARM v8. Most of your embedded devices, including that black router and the Raspberry Pis up to Pi 2, they are ARM v7. Some of the older IoT devices are ARM v6. The Pi 1s are ARM v6. At one point of time, ARM v4 onwards, ARM introduced what we call as the thumb mode. This is a very unique feature to ARM. This is probably the only CPU I know that supports two types of instruction sets under one CPU. By default, you have the 32-bit ARM instruction set. One key difference between Intel and ARM is that all instructions in ARM are fixed width instructions. Intel, we have variable width instruction. A NOP can be 1 byte, a call can be 5 bytes, an add can be 3 bytes. In ARM, everything is a 4 byte or a 32-bit instruction, fixed width. Opcode and operand is fixed. ARM v4 onwards introduced a smaller subset of instructions. The most popularly used ARM instructions were also available in what is called thumb mode, where a thumb is smaller than an arm. Thumb instructions are 16 bits wide, 2 bytes only. What is the purpose? Why is there a thumb mode? What's the rationale behind having a subset of instructions also available as thumb mode? So for example, add is available in ARM as 32-bit instruction, and the same instruction is also available as 16-bit thumb mode. Why is this important or necessary? Memory, yes. So your compiled binaries will be smaller, so about ideally half the size, but about 60% of the size. Yes.
Can the software have like both 32-bit and 16-bit?
Yes, absolutely. So your binary can have both 32-bit and 16-bit instructions coexisting together. You can switch between one another at will while execution is going on. You know, you might be executing 1, 2, 3, 4 instructions in ARM, then you flip to thumb mode and the rest of the instructions in thumb. No disruption, nothing whatsoever. And that's the beauty of ARM. They call this feature interworking. So ARM and thumb can be flipped almost instantly from one instruction to another. You can flip to ARM mode or flip to thumb mode. The assembly language remains the same, so you don't have to memorize different mnemonics for ARM or different mnemonics for thumb. You just have to tell the assembler that, hey, you know, output these instructions as 32-bit wide and those instructions as 16-bit wide. So the assembler will choose the correct opcode for ARM or thumb. You just remember the mnemonics as they are. Certain mnemonics are just not available in thumb mode. So, you know, some instructions, for example, there's some strange instructions that you won't see in thumb, but you'll see them in ARM. Right. Then ARM has something called conditional execution, which we will not get into too much of detail. but essentially every instruction can be predicated with a condition clause. So you can have add two numbers or add if greater than two numbers. It will look at the status flags, and the instruction will trigger only if these condition flags are met. Otherwise, it just falls through as a NOP. Then there's something called an inline barrel shifter. Basically, for arithmetic or numeric calculations, you get the ability to right shift and left shift for free. This is hardwired into the arithmetic and logic unit. So you don't have to pay an extra penalty for multiplication by 2 or division by 2. You just, you get it for free with every instruction, where if you don't want to use it, you set the bit shift to 0. ARM also has fully aligned memory access. That means all data and instructions must be perfectly aligned to 4-byte boundaries or 2-byte boundaries in thumb. You cannot have unaligned access, unlike Intel. And data in certain ARM processors, certain modern ARM processors, data can be accessed in both endian modes. By default, you always start by accessing data in little endian mode, but if you wish, you can set a flag to treat all data as big endian. I have not yet seen a practical implementation of big endian yet, but the feature exists. If there is a certain microcontroller you want to derive that uses big endian data, it's possible. Anyway, so the way we're going to do this is there's a little bit of theory that we have to get through before we can even start writing some instructions. So the first 45 minutes of the workshop we'll cruise through some theory, and then we'll have some exercises and some stuff to play with. The next thing I want to talk about are the ARM CPU registers. Intel has very few registers. ARM and every RISC CPU, for that matter, has lots of registers. Typically, you have a lot more registers. You have all the registers are numbered. You refer to them from R0, R1, R2 to R15. Each of these are 32-bit registers. Some registers have special purpose. For example, R15 is the program counter, PC, the equivalent of Intel EIP. So PC stores the address where the next fetch and execute is going to happen. R13 is the stack pointer, SP. What does a stack pointer do? Points to the top of the stack. You do push and pop. You do push, the stack pointer decrements, pop, the stack pointer increments. R11 is the frame pointer, pretty much like Intel EBP. What does a frame pointer do? Points to the frame, the base of the frame. Then any local variables are lower than the EBP, any parameters are greater than the EBP. So that equivalent is FP. There are two registers which the likes of which are not present in the Intel world. There is the IP register, which is not instruction pointer. It is the intra-procedural call scratch register, which is used to support something like far jumps. We're not going to talk about it. We don't care about it in this workshop, so ignore it. And R14 is a link register, which is very interesting. And actually, several RISC CPUs also have a link register. It's also called a branch link register. Now, to kind of give you a little idea about what this link register does, let me first take you to the Intel world for a little while. In Intel, if you have a function, what instruction is used to call a function? Call. Okay, why not jump? Why can't you just jump to a function? Brilliant. We want to push the return address onto the stack so that we know the breadcrumbs and we can find our way back, like Hansel and Gretel. If you do a jump, guess what? You don't know where you came from, so you don't know where to return to. Well, guess what? ARM has no concept of a call instruction. There's no call. There's only branch. You're going to do a function, branch to it, and then figure out a way of branching back. There's only 4 branch instructions in ARM. There's branch and exchange, there's branch and link, and there's branch and link and exchange. The link is the interesting part. So ARM is not that terrible, it will branch, but instead of the call instruction automatically pushing the return address on the stack, the branch with link instruction will save the program counter in a link register. So it's just like a temporary register to, like, you know, hold my beer. That's the link register. You say, here's my return address, just keep it while I go do this function. When I come back, I'm going to just branch back to the link register. So this is how functions are done in ARM. You might be already thinking that, okay, what if a function calls another function? Then what do? Then it is the duty of the function to preserve the link register. The CPU doesn't do it, so it's the burden is pushed onto the compiler. Like, okay, you want to call another function? We'll go save the link register yourself if you wish to return back. So typically in ARM, your functions are of 2 different types. We have what we call as leaf functions, which don't call any other functions. There are no branches from a leaf, essentially. And you have non-leaf functions, which are functions that call another function. The prologues for these functions will be very different. The leaf function has pretty much nothing, right? You've saved the link register, you return by branching back to the link register. A non-leaf function will push the link register on the stack, then go about its job, then it will call another function, the link register might be overwritten. But when that function returns, then you pop the program counter from the save link register, pretty much like the return will restore the EIP. So this is the purpose of the link register in a nutshell. And then R0 is the accumulator, just like EAX. R7 in Linux is used to sometimes store the syscall number. When you want to make use of kernel services, you invoke a system call, a syscall. Well, then R7 is used for the syscall. And lastly, CPSR is the flags register, current program status register. Now ARM has like several privilege modes and register banks and all. We're not going to get into that. This is just good enough for the user land viewpoint. Okay. And a quick look about the CPSR is you have 32 bits in the CPSR. The least significant 5 bits indicate which privilege mode you're in. Like 10000 will be user mode, and then the others will be like system mode, supervisor mode, fast interrupt, IRQ mode. There's several privilege modes. In Intel, you just have like user mode and kernel mode, ring 3 and ring 0. Here you have 7, 8, or even 9 different privilege modes on that. Bit number 6 is the thumb flag. If it is set, the CPU is in thumb mode. If it is not set, the CPU is in ARM mode. Then there are this Indianness flag. This 24th bit is the Giselle flag. At some point, the folks at ARM thought that Java was going to be a thing. So several ARM CPUs, yeah, kid you not, several ARM CPUs have built-in hardware support for Java bytecode. You flip this thing into Giselle mode, this becomes like a hardware Java machine. Except I've seen no documentation about it. I wonder why. And I have not met anybody who's really used Giselle mode. I'm hoping to find some folks from Cambridge who know how to use it and get them drunk, and then we can have shellcode in Giselle, which would be something insane. It's no joke. I'm sure it's possible. It's just like some research waiting to happen. If you guys find that out, please tell us how it's done, right? I mean, you can go publish it, claim all the fame, speak at 44Con, but at least tell us how it's done. Right. And then you have these flags, the -0 carry, overflow, underflow. These are set, typically the same type of flags as you have on Intel. They're set when you perform computation and all that. Now, whenever we're debugging or we're looking at GDB, how many of you have suffered GDB before? Terrible, right? It's terrible. Um, and GDB just throws up big bunches of hex numbers. Very hard to make sense of it. One of the things that we never bother in the Intel world really is like we rarely look at the flags register unless there's a condition. But in ARM, with every step along the way, you need to know which mode you are in. Like, especially when dealing with shellcode, you think like, oh shit, have we accidentally flipped to thumb mode or what? You must keep an eye on this flag. And typically GDB won't break these bits out to you separately. So you have to, if you don't have any special extensions or superpowers to GDB added, you will have to look at the CPSR yourself and see if the last byte is 30, then it is thumb mode, last byte is 10, that is ARM mode. We're going to use GDB with GEF, that is GDB enhanced features. It's a set of Python scripts written by Hugsy, and they make GDB great again. That's the catchphrase. But they basically, it's like, you heard of the Python PEDA extensions for x86. It'll decode the flags, it'll show you the stack frame, show you the little bit of code snippet. So GEF does exactly this, but it's cross-platform. Right. ARM instructions I mentioned, they're all fixed length, 4-byte ARM, 2-byte thumb instructions, inline barrel shifter, few instructions, many combinations. Thumb we talked about, what thumb instructions are. They're the most popularly used instructions. Talk about assembly language. This gives you a quick view into how assembly notation is written in ARM. A few things. You always have the opcode, the mnemonic of the instruction at the first. Then you have the target. If you're a big fan of AT&T assembly syntax, this will totally not make sense to you. But then again, you'll find that the whole world is completely weird because nobody can make sense of you either. This is, you always have destination, source, and other operands. I cannot read AT&T syntax. It kills me. So the first operand will always be a register, always. And this will be the target of any computation of any activity that you perform. For example, here is move. This is load immediate. Move R0, comma 5. All numbers by default in ARM are treated as decimal integers. And they will be represented with a hash. These are not hashtags. These are decimal number 5. The origins of this goes back to 6502 assembly, because 6502 also they used hash for all numbers, and they were by default treated as decimal. So this will set R0 equal to 5. So 5 gets loaded into R0. Some instructions will have multiple operands. Typically, Intel always has 2 operands. ARM instructions may have 2, 3, 4, or sometimes even 5 operands. And the way you read it is you read them from left to right. For example, here's the other instruction. Forget the GT part. Add R2, R1, hash 3. The way you read it is R2 equals R1 plus 3. In Intel, you'll always have the same register being added to. In this case, no. You can have 2 different things, and then they get added into a totally third register. Now, this GT part is the conditional flag. It is the same instruction add, but when you suffix GT to it, this instruction turns conditional, which means this instruction will trigger only if the greater than condition is met in the flags. Most used when you perform a comparison and then you do something like this. If, let's say, if you want to do a something like if it is negative, then do this. Like if, let's say, you take 2 numbers A and B. If A is greater than B, you're going to subtract B minus A. Sorry, if A is greater than B, you want to do A minus B. If A is less than B, you want to do B minus A. You do a comparison between A and B, then you do sub GT and sub LT or sub LE, sub less than equals. So only one of those two instructions will trigger based on the condition. And then the other, so you avoid excessive branching with these conditional instructions. And then you have instructions like move with S. This S is just to update the status registers after the result of an instruction. Let's not worry about that too much. Some conventions when writing assembly in the assembler. You have hash n, which is a decimal integer by default. If you like hex, you can always use the 0x notation to represent hex numbers, and you can use 0b to even represent binary integers. By default, whenever you invoke the assembler, all your code will be assembled in ARM mode. You can explicitly have assembler directives like .code 32 or .code 16. .code space 32 or .code space 16. .code 32 means all subsequent instructions will be assembled in ARM mode. .code 16, all subsequent instructions will be assembled in thumb mode. Right. I'll take over.
Not yet.
Okay. Popular instructions. This is pretty much the more or less all the instructions or a large subset of it. We kind of try to break them up into groups. So the main workhorse instruction is move, which is you load a value into a register or you move the contents of one register into another. Then all these blue ones are arithmetic instructions. MVN is like a negate instruction. You move a negative value. Add, subtract, multiply. There is no divide instruction. ARM doesn't believe in division because it's too expensive in hardware. So they say you guys rarely use division anyway. So if you want to do it, emulate it in software. Don't bother us. You do have LSL and LSR, which are logical shift left, logical shift right, the bit shift instructions. You have arithmetic shift right. There's no arithmetic shift left. It's all LSL is equal to ASL anyway. And you have rotate right. There's no rotate left. If you want to do a rotate left, do a very large rotate right. So ARM tries to save on instructions if they're not necessary, because they don't expect you to write the assembly by hand. They'll always expect a good compiler to generate efficient RISC code. Basically, if you have a compiler that's really rotten compiler, RISC CPUs will be terrible. But if you have a good optimizing compiler, then RISC CPUs will be very, very fast.
So how many instructions are there?
I think this is pretty much it. And then there are some extensions like vector processing instructions.
Around 100.
Okay. I'm sure because I didn't even read.
Not as much as on Intel.
These are the bitwise instructions where this is compare, which will basically set the flags when you compare two values. Then you have AND, bitwise AND, OR is not a typo, the opcode is ORR, and I always screw up when writing the OR instruction. The assembler complains, I say, okay, damn it, I'll go and fix it. But the more annoying thing is like they call it EOR and not XOR. Somebody is a Winnie the Pooh fan, for sure. This exclusive OR is EOR. Is another thing that I always make a mistake with. So these are bitwise. These ones, the red ones, are load store, LDR and STR. This will load a pointer into a register. STR will store a value from a register into a memory address. So this is where you read memory, the contents of a memory by address into a register. This is where you store the value in a register into an address in memory. You also have LDM and STM. You can do load multiple and store multiple. So you can like read 8 elements of a time and populate them in 8 registers in one go. And you can write them back You can write multiple registers back to memory as well. Even push and pop, these are also variants of load store. In Intel, you can only push one element or pop one element at a time. In ARM, you can like push n number of registers and pop n number of registers in one go. Then the 4 branch instructions I already talked to you about. There's a simple branch which is like a jump. This branch with link. Then you have branch and exchange. Exchange means flip the thumb bit if needed. If you're going from an ARM function to a thumb function, it will flip the bit. If you're going from a thumb function to an ARM function, it will also flip the bit. So exchange will switch the mode only if needed. You can also branch with exchange from an ARM function to an ARM function and no bit will be flipped. It will look at the address and figure out whether it's an ARM address or a thumb address and do the bit flipping only if it is going from one mode to another. If it is the same mode, it's not going to flip bits. So there's a big confusion sometimes that when you begin writing assembly, you think the BX will always flip the mode. No, not necessary, only if needed. And BLX is like branch with link and exchange. So you save the return address in the link register and exchange if needed. And lastly, the SWI instruction is the same as the SVC instruction. This is supervisory call or a software interrupt. This is like trap to kernel. Use it when you want to invoke a syscall. It's like an interrupt. Okay. So this kind of takes us through the basics of registers, ARM CPU, and instructions. What we're going to do next is just put the first little bits of assembly together. And then we will study, we'll just write our own assembly. Then we will do a very simple Stack Overflow exploit. And then we'll write the exact shell code for it. So that's how the rest of the workshop's going to go.
Yeah.
Okay.
We already started writing the assembly program, like right now. Or should
We'll
we
do
go over
the
the theory.
we'll do the first. Yeah, we can just go with the first bits of the assembly, like just
the
simple
first
assembly,
theory,
the
like-
first and all, and that we'll try it out. We'll try it out on the Raspberry Pi. At least just get the assembler going and run one program GDB single step, and then that should be good.
Yeah, so let's get right into it. Oops. Okay. So this is a structure of a very simple assembly program. Saumil, can you? Yeah. Right. So our code goes obviously into the text section, which means that we need some starting point. Our default starting point is underline start, and this is where our code goes. So we have to indicate that we start with our mode. And we do it by specifying .code32. Later we will switch to thumb mode, and then we need to indicate that we are in thumb mode, so we will write .code16. All right. So this is how we assemble our assembly program. Just 2 simple commands, as the assembler, then the linker, and then we get our program. How we inspect our assembly code, very simple with object dump. Most of you might know the tool already. And yeah, GDB, very popular tool. Some of you have already some experience with GDB. We will cover some basics, so we will just load our program into GDB. We set a breakpoint at underline start and we run it. Right. So on the right, you see the basic commands that we will need in GDB. How to set a breakpoint. Either you can write break with the start. You can just write B. Run, continue, or just C. You can use step E to step into an instruction, or next E for next instruction. Info registers will show you all the registers. However, you will see the registers in GDB anyway. Yeah, so, and this very interesting syntax you see here is basically the X stands for examine, and 20, like 20, we want 20D words in hexadecimal format. That's what the second X stands for. Right, so very simple. This is how it looks like. It looks a little bit more fancy on our, like, yeah, on the real GDB with a little bit more colors. But here you can see all the registers. So everything, we have a good overview over the registers. And here, how Saumil already told you, the flags. The most important part for us is the thumb flag. So as soon as we are entering the thumb mode, this will be bold. And this will indicate that we are, in fact, in thumb mode. Here you can see the stack. Obviously, the stack pointer points at the top of the stack. And here goes our code. And PC points to the next instruction that will be executed. PC on ARM has its nuances. It's not as straightforward as on x86. So usually PC points to the next instruction. However, if you disassemble, so if you would actually write an instruction which says move PC into a register, and you just before executing this instruction, you would look at PC and just memorize that address, and then you would execute that instruction, and not the same address would land into that register, but the next after that. This is because older ARM versions fetched 2 instructions ahead, and well, backwards compatibility for these reasons ARM kind of retained that. So if you don't get confused in case you encounter that, and it's confusing, but yeah. So yeah, if we step E or next E and so on, so this is how our registers change. It will indicate with red, right? So this is the very basic overview of a very first assembly program. I guess it's not necessary that they already start writing this down.
No,
right?
no. This is, I mean, basically, the template is given. This is just to kind of give you a walkthrough of it.
Yeah.
Let's do this. Let's do this on
Let's do it?
Yeah, let's do it.
All right. Let's jump right into it.
Let's jump right into it. Right? The heck not.
Yeah, why not? All right. All right. I will. Should I? Here. Yeah, that's all right.
This is when we wish we had the dual screens. When we teach, we like to have 2 projectors. It's true, actually. It makes a world of a difference. Okay, so I'm going to try one-handed typing, and
I can hold your microphone if you want.
no, it's going to be really weird.
Yeah.
Okay. Ouch. Okay, while I get set up, just a couple of minutes. Any questions about ARM stuff so far? Anything confusing? Anything doesn't make sense? Yeah, all good.
I mean, ARM is beautiful. It's much more simple than x86
Truly is.
once you know it. I heard one person actually said he finds ARM assembly much more confusing than x86. I can't understand that, but
You spend a lot of time in x86.
yeah,
Yeah,
I believe, yeah.
we get tuned to the Intel way of thinking, then this is different. And,
Yeah, you find it more simpler than
Very simple. It's very simple.
If that's your first assembly language, then it's awesome and it's really simple. Should we cover some of these more?
Okay,
There are
yeah.
some instructions.
Yeah, let's do that.
Right?
Let's
Yeah,
do that,
we
and then
can-
we'll get into the thick of things. How about that?
Yeah.
Go ahead. Go ahead.
Right. So these are some, or is anyone? Yeah, everyone is kind of setting things up, but just in the background. So these are some arithmetical logical instructions. Simpler, I guess. I don't have to explain that. Yeah, Saumil already mentioned branches. So we have 4 different kinds of branches. We have a very simple branch where you just branch to a specific offset, where we just branch to PC plus offset. Then we have BX, branch and exchange. This is when we actually want to exchange our modes, basically. BL, which first saves the value of PC into LR and then jumps, or like then branches. And BLX is just a combination of BX and BL, so it will also exchange but also saved PC to the link register. Right. So what we will need is BX for our example, because we will need to jump. We will need to, jump to thumb mode, because
Now, this is a good time to also ask ourselves, how does the CPU know when to switch modes, right? An instruction, let us say the instruction is at address 8060, just making it up. How do you know this address contains an ARM instruction or thumb instruction? You don't, right? It's just going to be bytes. So, well, the assembler will have created these directives. So, if you're branching to a label that contains a thumb instruction, the assembler will generate an address which will force the CPU to go to thumb mode. This can be a little confusing at first. Step back a little bit. In ARM, I told you that all instructions are either 4 byte or 2 bytes. And all access to instruction is fully aligned. So your program counter can only have even numbers, multiple of 4 or multiple of 2. So what the engineers at ARM did cleverly is they used the least significant bit of the program counter itself to force a thumb change. So if you take address 8060 and branch to it, the CPU will be in ARM mode. Least significant bit is 0. But if you take address 8061 and branch to it, the CPU will flip to thumb mode and clear off the least significant bit. So your program counter will still be 8060, but you'll go to thumb mode. So this is what we mean by this statement. When the branch happens, you inspect the least significant bit of the target program counter. If the target address is an odd number, set thumb mode. If the target number is an even number, set ARM mode. This is how the modes switch, and this is one of the most confusing things about ARM branches when going from ARM to thumb and thumb to ARM. Yes, your question. Go ahead. Binary exponential back off.
So if you can use the memory address to identify the mode in which the CPU is executing, and what's the point of the CSPR bit?
It's the CPSR.
Yeah. So when is that used?
The CPSR will be set when you go to thumb mode.
Okay.
Yeah. So basically, when you branch like this LSB equals 1 will turn that CPSR flag on, and then the CPU will decode thumb instructions. Your question.
Yeah, I was just going to ask it. So, does the assembler always offsets the
No. The assembler will never offset the instructions. So the instructions are not at an odd number. The instructions are still fully aligned. The branch values will be at an odd number.
Oh, because they're always aligned.
Correct.
Right.
Correct. So the branches will seem to go to an odd numbered address, but it will just flip the bit and back to even number. The LSB will be cleared off in the actual PC.
Right, so we will see an example of that, but in theory, how this will look like is that we need to branch an exchange to something, and we will branch an exchange to a register. However, in that register, we will first put PC plus 1, right? The least significant bit. So this is all. Those are two simple instructions how we prepare, and then we basically just branch and exchange, and we are in thumb mode. It will be very trivial. Once you see it, it's very easy. So don't get confused too early. All right. So yeah, as Saumil mentioned, ARM is a load and store architecture, which means only load and store instructions can access memory. And here are some examples. You don't need to memorize all of them. It's just like for the overview. Also, these are not all variations.
Actually, there's only 2 instructions in this slide.
Yeah.
There's just 2 instructions with 5 different variations each.
There's also load and store multiple, which works slightly different. But for now, you don't need to remember load and store multiple or learn any of that. So here is an example. So when we use load, we want to load something from memory into a register. When we use store, we store something from a register to a memory address. That's it. It's just that. So here you can see something from memory will be stored into into R0. And here, whatever is in R0 will be stored at the memory address you find in R1. And what we will need in our example is, for example, the store bytes, because we will need this one instruction to store a byte, the specific location. And I guess we will also need to use load for one simple example. But for now, that's all you need to remember. I mean, we all know it's late, so it's okay. You don't need to remember.
So by
everything.
default, the load will be loading 32-bit values. Load H, so LDRH, STRH, 16-bit. LDRB, STRB, 8-bit. 3 modes, either just directly the address is referred, address plus numeric offset, address plus register offset. These modes are very useful when you're walking through an array, base and offset and things like that.
All right, so loading immediate values or storing them, loading them into a register is not as trivial as in x86. There are restrictions, a lot of them. So we have, not sure, should I go into a lot of detail or?
No.
All right, okay, so long story short, we only have 8 bits. Plus, we only have 8 bits for the immediate value, which means this is a problem. We cannot load, we cannot load a 32-bit value into a 32-bit register. It's just not possible. Assembler will complain. It will say, what is it, error? Something with invalid constant. So if you encounter that, you know exactly what's happening. But there are bypasses for that. So is it already at the next slide? Yeah. Yeah. So basically, there are 2 ways. First, you can either split your number and then piece it together, or you can make use of the literal pool. And the literal pool is just a section, it's just a region in memory in the same section. It's basically also part of the code. And we can use a specific syntax that we will later see. It's not in the slide right now, but all you need to know right now is, let's look at an example. So, let's say you want to place a string or a constant into the literal pool. Now, you need to access it somehow. How do you access it? For that, we need PC relative addressing. What that simply means is that we need to calculate the relative distance or offset relative to PC. And since we know that PC behaves a little bit strangely, that we don't start counting from the next instruction but 2 ahead. So again, this is the literal pool, right? This is our PC.
Just one second.
Yeah.
Just back by one thing. Kind of give you an analogy of what the literal pool is. Okay. You're not allowed to store. Anybody done basic programming, like hardcore basic, 8-bit basic? No, you guys are all Python guys, right? God, what a
Or
world.
maybe they're just all young, very young.
In basic, there used to be. Oh God, this makes me feel terribly old. Right? I am the 44 and 44 con, really. In basic, there's a statement called read data. You heard of it? You write, like, at the end of your program, you write data. Then all the numbers are in this data section, and every time you read, it will just read from this data. Think of the literal pool exactly like that. No other programming languages have this feature of read data, but I kind of think of a literal pool as that analogy. Let's say this is your function, or this is the end of your subroutine, and your subroutine is using large constants. The assembler will stick these large constants at the end of your subroutine in the code itself. Down below might be another subroutine. So between subroutines, you'll have these little literal pools with values hanging out. Now, as you're going through the subroutine, you say, okay, here I am, I need to load one of these into this. So the pointer at this address is the program counter. And that is why you take program counter plus an offset to get to the literal pool. And you'll be wondering, like, okay, program counter plus 12 is only going to get us here. Then how the hell is the literal pool over there? It's 4 aligned already. So yeah, that's what
Yeah, so
we're going to talk about.
exactly. So since the PC is not really where the PC should point to, so we always have to start calculating from the current instruction plus 8, then we start calculating. So basically, count instruction plus 8, and then we basically 4, 8, 12, and we land here. And, wait.
Why current instruction plus 8? Because it is the way it is.
No one knows.
So, well, basically it's not, think of it like this. It's
Why the
not,
12?
sorry?
A serious question.
Yeah, one second. I want to just kind of wrap this plus 8 thing. Don't think it of PC is equal to current instruction plus 8. Think of it as 2 instructions below this one. If it is in ARM mode, it is plus 8. If it is in thumb mode, it will be plus 4. The true reason is the old ARM CPUs had a 3-stage pipeline. So the PC, there will be PC will be already two instructions would be prefetched. So therefore it would go to the third one. But now, of course, you have this multi-stage pipelines, but this thing was just kept because of the way it was once upon a time. And that's why whenever you have the PC used as an operand. Always take PC, the address of PC plus 2 instructions below. Your question, why plus 12? So what's going to be the effective PC over here? 8100 plus 4, 810 plus 8, so 8108. The literal pool is 4, 8 and 12 bytes further. So add an extra 12 to this.
So yeah.
When you're writing shellcode, when you're writing normal assembly, you can use some macros to automatically generate literal pools. But when we're writing shellcode, we'll have to write the literal pools and the offsets manually.
So in our shellcode, we will have one instruction that will look like this. This is why we are covering it.
Okay, question. The next one, at address 8104, you have the instruction add R1, PC, 12. What will be stored in R1? Nope. Let's read how this instruction plays out.
Plus 8 with C plus.
R1 equals PC plus 12. What will be the value of PC? 8104 plus 4 plus 8. So PC will be 810C in here plus 12. So PC will be, this will be 8118. R1 will have the value 8118. You're not dereferencing it. This is dereferencing it. We're not dereferencing it. So it's just a pointer. See how confusing it gets? So every notation, every symbol is very important. Brackets, no brackets. What do we do? Simplest way is just go back to first principles, read the instruction and just put it down on paper.
Right, and always remember, everything must be 4 bytes aligned. Which means that if we are in thumb mode, then we don't calculate it with 4 steps, but with 2. So we can end up having something not 4 byte aligned. In that case, we will just add a knob. There isn't really a knob in ARM, so we just add a useless instruction. So that's that. So in this case, we add a knob because we are, just imagine this is thumb mode, and we just don't get the 12. Really, we are ending up at, right. Little pool, 4 byte aligned, we add an extra knob.
So one sec, just 2 things to remember here. This address of the literal pool must be 4 byte aligned, and this number of the offset must be 4 byte aligned. That's it. Nothing more to that. If it's not fitting, you have to put a knob in between to kind of make it fit together. This only applies to thumb mode, not ARM. Yes.
Okay, so I'm sorry, you said to answer this. So every line has to be 4 bytes. There has to be like less than 4 bytes in between each other. So every basic like memory address has to have 4 bytes.
No.
Is that what you mean? No.
No.
Okay.
So look at the. Yes, let's study this code. Look at the addresses. This is plus 8 plus AC. These are 2 byte addresses. Right? This is 8, 10, 12, 14. These are thumb instructions. You see the opcodes, the sizes are also 2 bytes. So in thumb code, everything will be 2 byte aligned. But offset of literal pool, this value must be 4 byte aligned, whether it is ARM or thumb.
How do you represent that 4 bytes? The 12.
The 12.
Yeah, but how do you represent that 4 bytes?
Which I didn't get the idea.
Okay, all right, cool. All right. Now my
It's
bad.
just a multiple of 4 bytes.
Okay.
Yeah.
So the literal pool appears always at the end of the function.
Hmm?
Right? So
Yeah.
in this case, if this was the real code,
Yeah.
then how would the
Well, typically at the end of every function, you're going to return anyways.
So it would return automatically.
No, there will be a return instruction.
Ah, okay, okay. So it's missing here.
So here is we're not returning, but we're invoking an interrupt. So it's again going to go away. From the ISR, you return away.
Yes. Speaking of invoking, you want to make the x86 part?
Sure. So now again, let's kind of think of the focus to shellcode. For those of us who've written Intel shellcode, what does shellcode really do? What do we do in shellcode? We know there's several types of shellcode. There's exec shell, there's bind shell, reverse shell. But effectively, what are you doing in shellcode? You're making use of operating system services, either to launch a binary or to open a socket, to establish a connection, change the IO stream standard in, standard out. All these are syscalls. So effectively, your shellcode is nothing but set up some parameters, invoke a syscall. Set up some parameters, invoke a syscall until you get the activity that you want. So how do syscalls get invoked in Intel? You either push the parameters on the stack, or some operating systems also have the parameters loaded in registers. The syscall number goes into EAX. So every operating system will have several syscalls, hundreds of syscalls. And each of them have a number. Like number 11 means execv, number 63 means dupe2, number 281 means socket. So whatever service you want, you put that number into the accumulator in EAX, and then either invoke sysenter or interrupt 80. This will trap to kernel mode. The kernel will process the syscall for you and return. In ARM,
So, should I? Yeah. Okay. So in ARM, this works a little bit slightly different. So whenever we want to invoke a system call, we first need to load all the parameters into registers. Once we have done that, we need to invoke the system call by first figuring out the syscall number, then moving it into R7, which is a specific register for that purpose. And then we invoke the system call. Very simple, very simple. So let's look at an example. Let's say we take write. So how many registers will we need for the variables in this example? Yeah, 3. So we will use R0, R1, R2, and then this is called. This looks like this. So very simple. We just store the 1. We move the 1 into R0. The string reloads. The pointer to the string reloads into R1, and then the bytes, the length into R2, and then syscall number 4 of write into R7, and we invoke. The same we will do with our shellcode. Well, we won't invoke write, but principle is the same.
so effectively your ARM shellcode is going to be exactly like this. You're setting registers R0, R1, R2, or R3. Set R7 to whatever value you want is a syscall, SVC0. And then you get the syscall code.
Does this imply like a maximum number of parameters? Because there's only so many registers.
So yeah, there's only, well, there's 15 registers, but we can't use the last 5. They're special. In ARM, generally functions will pass parameters via registers. Up to 4 parameters will be passed by R1, R0, R1, R2, R3. If you have more than that, then the rest of them can be spilled over on the stack. That is the ARM architecture procedural call standard. So compilers will choose if your function is 4 parameters, the compilers will generate code for register bound parameters. More than 4, then you'll spill them onto the stack. If you have to have a syscall which requires more than 6 parameters, then you catch hold of the developer and teach them a lesson in modular programming. This is rubbish. So no, but no syscall uses more than 6, at least not that I've seen. Right.
All right, your turn again.
Okay. So let's play with some assembly. Let's assemble some code and GDB it and get familiar. Then we will do a quick crash, and then we'll start getting the shellcode in place. This is readable? Okay, so I've just set up my working directory. Let us look at this one, first.s. That's your first assembly program. Now you can use VI or Nano if you like. If you don't know any of these two editors, then sucks to be you. I don't have Emacs on it, and I'm not going to apt get it. I'm so sorry. Vim, yeah, I mean, I think I have Vim on it. It's VI, Vim. What's the difference? Okay, so this is how we are going to compile all or assemble all our code. Whenever I use the word compile, think assemble. Every code begins with section.txt. Whenever we are writing assembly, we will create an ELF binary to test it out. But when we're writing shellcode, this will be then injected in a payload somewhere. However, for testing, we'll still put it as an ELF binary so to test whether it works or not. So we'll always begin section text and define a global label underscore start. This will be the entry point of the ELF binary, and then all your instructions will fall under start. So here we have move R0, 2, add R1 equals R0 plus R0, and this BKPT is just a breakpoint. So that's the end of your code. You'll run this in a debugger. There's no standard in, standard out. So whenever we're testing our code, we'll just GDB this and single step through and see what changes happen to the registers. Right? So very simple. I'm going to now assemble this code. Now let's be very careful in the assembly. AS first.s -o first.o. This will generate the object file. If you want to check the disassembly, you can disassemble the object file by using object dump. Object dump, dash D first dot O. And this will show you that, okay, this is the start. All the addresses are relative because it has not been linked. Here you see the relative offset 0. This is the instruction in encoded form, 4 bytes, and these are the mnemonics for that instruction. Each instruction you see is 4 bytes long. The move, the add, the BKPT. This is how object dump looks like. Now let us link it. So we're going to use the linker LD. While linking, always remember, this is very specific to shellcode. Always remember to link with uppercase N as the flag. So LD-N first.O -O first. This will generate an ELF binary. What does this -N do? It will turn the text section into writable memory. By default, all binaries have the text section read and execute. The -N turns it back to writable. Why do we want it writable? Because our shellcode is going to be eventually injected in writable memory. We might modify some data in the shellcode itself. So that is why we always want to use the -N. Just make that a rule. Whenever you're linking shellcode and testing it, always use LD-N. So now this is linked. And you will see that you have a compiled binary present. Once we have the binary present, we're going to debug it. GDB first. And if we run it, it's just going to straight away crash. The way we will test our assembly is typically set a breakpoint in the beginning, and then we will single step the instructions. So I'll say break underscore start.
Is everyone following?
What I'm going to do is I'm just going to open a little notepad and start typing the commands on the side. So we just have a little list of it. Do it right here.
You can also change the microphones if you want.
That's all right. I think I'll Okay, so just to kind of give a little command reference on the side to make things a bit easier. Okay, so we set a breakpoint at underscore start, and now you just type run. And here you get the, all this is nice GEF stuff. So you're at the breakpoint. Let me just give you a quick tour of GEF. It says starting program, breakpoint is at 8054, that is the entry point of your ELF binary. This stuff is the stack section, and here you see the registers. Your program counter is at 8054. By default, you're in ARM mode. All your registers are 0. And these are the instructions that you're going to now execute. Your current instruction is move R02. You're then going to do a step I. That will then set the value 2 into R0. All modified registers you'll see in red color. The next step I will do the add. You see R1 as 4, and then you hit the breakpoint. You can even do continue to let it run further. And then it'll say it's crashed because now it has hit the breakpoint. It's clear? All good? Okay. Once you're done debugging, you do Q to quit the debugger. So this is how typically your test session will be. Whenever you're playing with assembly, this is your test session.
Continue with the slides.
Just took the crash and all that.
Yeah. Or what comes next?
Okay, any questions about GDB or assembly or the process or things like this? Now we're going to see a very quick crash, and we're going to write a shell code for the crash. So I'm going to just show you. How many of you are familiar with Stack Overflows? That's all right. Just the overall concept of Stack Overflows, right? So here's your classic spot the bug thing. Where's the bug here? String copy. This is what's paying our salaries for 30 years now, right? That's why we're in business. Good old string copy. Somebody's wearing a shirt, string copy and string cat. That is the most fantastic shirt I just saw. I just saw that walking past here. So, what's going to happen if S is greater than 128? It'll overflow the buffer. It'll go past the stack frame. It will overwrite the saved program counter in the stack. Why will the program counter be saved on the stack? I thought it is only saved in the link register, isn't it? So is function 1 a leaf function or a non-leaf function? It is. How many you say not a leaf function? How many of you say leaf function? Okay. Well, here it is not a leaf function because it's going to call string copy, right? Function 1 does invoke a library function called string copy, so it is not a leaf function. And therefore, function 1 will save the link register, push it on the stack, and when it returns, it will pop the saved link register into the program counter. So we will overflow the frame. We will get control of the program counter. We'll get a segmentation fault. We'll get a core dump and all that, right? And towards the end of our crash, let me show you what the crash looks like. We'll see this is how the crash is. This is like a very quick crash course in Stack Overflow. We have victim1.c over here. It's the same thing. Let us make victim 1. It's going to compile the code. I've cheated a little. I've turned the stack executable and all that. So kind of just get us through the workshop really. As I don't have time to teach you return-oriented programming. Make victim 1. Then let us run it. But we have to be polite first. We can't crash it yet. See victim 1 hello world. And it says okay, so that means the program ran, it finished. Now we can be rude. Now let's do victim 1 hello world and like
Endless screaming.
yeah, endless screaming. 2 line full of A's. And we get segmentation fault. Now if we do this in GDB, let's see what we get. Actually, there's a file which we'll use. Now let's just do it this way. GDB victim 1. And then you just do a run with endless screaming A's. 2 line fulls of it. There we are. What do you see? Classic crash. Yeah. If it was Intel, you'd get EIP equals 41414141. If it is ARM, what do you get? 41414140. This is how you tell if somebody really knows ARM exploits. You tell them and you go to them and say, oh dude, I have this proof of concept that gives you PC equals 41414141. If they fist pump you, they know nothing absolutely. You suck, go away. You'll never get 414141 in ARM. Right? Why is it 41414140? Exactly. That's right. You tried to make it jump to an odd numbered address. It jumped to 41414140 and see what happens to the mode. Now it is thumb mode. So we control the return address and we also control what mode we can flip it in. Okay. So this is what we get. This is the overall crash. And this slide represents what you get in the crash. This is your typical payload, right? You have your buffer, then this blue part is the overwritten program counter, and your stack pointer will now be pointing to the end of the frame, where you also have the continuing part of the buffer. How are we going to now play this out? Let's say you're now writing an exploit. Where will you place the shellcode and how do you jump to the shellcode? So we generate the pattern string. We can do the pattern thing. Okay, I just say that this is offset 128, for example. Let's say the offsets are known. This is offset 128, this is 132. Where does the shellcode go? Blue part or orange part? We can put the shellcode over here, nicely aligned with the stack pointer. And if it was Windows, what do you do? Or Linux, or Intel, what do you do? How do you get to the shellcode? You return to jump ESP. So here you find the address of a DLL or a library and you return to jump ESP lands here. off you go, shellcode's over, right? We'll do the same thing in ARM, except we don't have jump ESP. What instruction do we return to? To the stack pointer. So what instruction will that be on ARM? There's no jump. Branch. BXSP. That's the instruction we want. What idiot compiler will generate a BXSP instruction for you? Why did jump ESP work in Intel? I mean, jump ESP is also a complete bizarre instruction, right? Think about it. Who the hell wants to jump to the stack pointer? Why should this instruction even exist? What makes it exist on Intel? Why do we find it with MSFP scan or MSFL scan? And so many of them. Maybe. No, not really. We just need the byte sequence. Exactly. In Intel, you can have unaligned access. Any 2 bytes become jump ESP. We're good. Even if they're like the last byte of one instruction, the first byte of the next instruction, if you can take them and just compose a third instruction out of it, that works. Well, in ARM, you can't do unaligned access. So in that case, what we do in ARM is, just to cut a long story short, instead of looking for 4-byte ARM instructions, we force disassemble a binary into thumb mode, whether it's thumb or not. Because you can always split an ARM instruction into 2 thumb instructions, and if any of those 2 bytes becomes BXSP, we're good. So we'll find a BXSP and then we will return to the stack. And this is where our shellcode goes. We're only focused on the shellcode right now. Forget about how to get the BXSP. What we're going to do in the shellcode is we're going to now return to bin.sh. We're going to exec bin.sh, that's our shellcode. Okay. So, some goals of writing shellcode. The shellcode must be self-contained. That means you can place it anywhere, use it anywhere. As long as it is Linux and ARM, this shellcode should run independent of the Linux distro, independent of the kernel, independent of the library, independent of the target being exploited. Which means we cannot have any absolute address, we cannot have any library calls, everything we need to access is via syscalls, and to make matters worse, it has to be free of null bytes, otherwise string copy stops. So these are some of the objectives which we will use in constructing the shellcode. Next one. Right, so this is how we're going to do it. We're going to find a BXSP instruction, place the shellcode over here, and then branch to it. And now we will just jump over to the shellcode.
Do you want to do this for me? Yeah. All right. So our very simple shellcode will be just a simple, well, system bin.sh. However, system bin.sh invokes exec ve. And this is what we will be paying attention to. And as you can see, we will need 3 parameters. Again, like the write function, we will need 3 parameters. And we will need a syscall number, which will be 11 in this case. So, again, very simple. First parameter, the string goes into R0. Then we make it very simple. We will just leave the next 2 0, and then we need R7 for our syscall, and then we invoke it. So this is how exec v looks like, right? And this is our simplified version. And we will translate this into ARM assembly.
Let's step back.
Yeah.
All we have to do is these 5 operations, right? Set R0 to the pointer of bin sh, set R1 and R2 to be 0, set R7 to 11, and then the next instruction is svc0 to invoke this syscall. What should our assembly look like? Let's forget this one. Okay. These 3 are easy. What do? Move R1, comma 0, move R2, comma 0, move R7, comma 11, and svc0. So, hey, you got 4 out of 5, not bad. This is 1. Okay. Keep that in mind as we go ahead.
Should we make this slide or rather practically? Because this is already.
Sorry, does the, if you move 0, does that not you move the null into
Does that, yeah. So if we move R1 equal to 0, that will cause a null in the argument and there will be a null byte. Yes, there will be.
And we will denullify it.
So we'll always take 2 steps to writing shellcode. First pass, let's just make it work. And second pass, we will denullify it. So first, let's just focus on making it work. Then we'll get the nulls out. Okay. So let's just try it out. There's a very simple script over here, exec arm.s. This is your bare bones exec shellcode. We will link it. I have made a mistake in here. We should link it with -n. So keep that in mind. But let's see how it is done.
So yeah, again, you see what we encountered with the PC relative addressing. This is what we will need because we will need to place our string into the literal pool, and we just use .ascii and write a string ending it with a null byte. And then again, where is our effective PC? 2 instructions ahead, right? And then 4, 8, 12.
So R0 will be PC plus 12. R0 will point to bin sh0. Then you have R1, then you have R2, then you have R7 is 11 and svc0. Let's try it. Let's assemble it. Let us then debug it. Got it? First, let's test if it works. We'll run it. /exec arm. Boom, you dropped into a shell. Okay, this works. That means the exec worked. Heck, we got the code and the syscall, right? It didn't crash on us. We exit it. Works for everyone? Okay. Now let's look at the opcodes in there. Now we're going to object dump it.
Now, what do you see? Yeah,
Too many of
lot
them.
of them. A lot of them. Too many.
There's 1, 2, 3, 4, 5, 6, and 7. 7 nulls. Right. How do we denullify these thoughts? So the zeros, we get rid of it. Instead of R1, we just EOR, not XOR. Remember that, eh? EOR R1, 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 EOR R2, R2, R2. That will get rid of those nulls.
Yeah, but
Let's try it. Let's try it.
yeah, or let's try it.
So these moves go. And now we're going to assemble and link it again.
You can also use sub, would have the same effect, right?
So for those guys, we got rid of those nulls. So this, yeah, this is okay. This got denullified. This got denullified. What about this one? Add R0 PC12. We have to have it in R0. There's no other way. Because R0 is the first parameter.
So
This is the R0 part. And this is the 12 part. Sorry, you were saying something.
So how do we generally decrease the likelihood of having them? Because now we have those 32 bits.
Yes.
Right. So
precisely.
you
Dot code 16.
you decrease the likelihood of having them, and then you can denullify the rest of them. Yeah.
But the thing is, your shellcode will always start in ARM mode. Even in the middle of an exploit, it will start in ARM mode. Why? In fact, when you branch to the stack pointer, you're going to branch in thumb mode because there's a thumb instruction. So you'll use an odd instruction. But when you return to the shellcode, what will your value of the program counter be? Odd or even? Always even, because your stack pointer will be at an evenly aligned value. So it doesn't matter what mode you were in, you will always be, when you enter your shellcode, which is aligned at the stack pointer, always be in ARM mode. Always. So yes, you want to write your shellcode in thumb, but you have to begin in ARM. How are you going to solve that bit?
Two instructions, basically.
Dot code system will emit the code in thumb, but how do you force the mode to go to thumb when executing?
So you start in ARM.
Branch.
And before that, we branch to what?
Branch to the, all the increment above.
So we branch to a register, but what is inside of that register?
SP, like the alt, like the plus one, SP plus one.
The least significant bit, right? Yeah. So
Not this one.
yeah. So in our last example, oops, we would use to jump to PC. However, if we add PC into a register +1, right? Huh? What was the question? Other words. Right, should we just make an example?
Yeah, we'll do that.
Yeah.
So let's look at execthumb.s. That's precisely what we're doing.
Right.
Here,
So, yeah.
of course, in execthumb, I have not denullified this bit, so I'll denullify that. But in the meantime, you can just
Right.
explain it.
So here again, we start in ARM mode. So we need to indicate this with .code32, and then we just use R3, and we add. First, we add just these two together and place them into R3, which makes the least significant bit 1, and then we just branch and exchange to that register, and then it will just jump into, like, switch into thumb mode. And then we need to indicate that we are in thumb mode, basically in our assembly program with .code16.
So is this switch to thumb mode clear? You just add 1 to program counter. The effective program counter will be 2 instructions below. So 1 and this one, but this will be then taken as an odd address. When you do a BXR3, you branch to it, you're now in thumb. So quick ARM to thumb switch. Now, what happens to the PC relative address here? What is your effective PC in this add instruction? 2 instructions below, then +2, +4, and it would, if this move wasn't there, it would be +6, and that has been SH. But +6 is not a multiple of 4. So you have to have this junk NOP in there. There's no NOP instruction, so just move R5 into R5, treat it as a NOP. And then you have the bin SH. So that'll be +8. And that's your new PC relative address. So now let's check this out. Let's check out what we have. Let's assemble exec thumb and see what we get. Let's first test it. If this doesn't work, then we have a problem. If this works, then we'll denullify it. Okay, exec thumb works. Getting there. Let's object dump it and check. check out the disassembly. The first two instructions are 4 bytes, but no nulls. Now these are all 2-byte instructions, no nulls until, here's a null, SVC 0.
You allowed to call the content of a register.
We can't do SVC R1 or something, no, it has to be a constant. I'm sorry? Well, nobody said it cannot not be 0. So, so we just try with SVC1 and the damn thing works. It does. In most Linuxes, it actually works. Ideally, it's supposed to be, like an ideal implementation should pay attention to it, but the Linux kernel ignores anything after SVC. Say, okay, SVC1, doesn't matter, the same syscall table is available. So we'll make this as SVC1. And then this last null byte still remains. Is a string terminator.
You do null byte bombing.
Which?
So in Intel you can do null byte bombing where you put the string in with say some like X or something.
Right.
And then you overwrite it with the X or something.
Precisely. So we will put some character like X instead of the null byte, and then we overwrite that with a null byte. Yes, that's precisely what we'll do. So let's edit the exec thumb and make those two changes. Let's ponder upon how we're going to do this null byte bombing bit. First, let me just get rid of this SVC0 to SVC1. Okay. And then last, instead of bin sh0, I'm going to make it bin shx. Now, how do I override this x with a null byte? That's it, like one last step remaining and your code's done.
So we had this one instruction when we covered load and store. There's this one instruction called store bytes, right? So this is why we linked it with the uppercase N. And we will use that instruction to store a null byte at this exact place where we now place the X. And where do we get that null from to store it to, right? But we already have it. We have it in registers, right?
R1 and R2.
Yeah. So you just take that and just put it there.
It's going to be store byte R2. What's the target address?
Now again, with PC relative addressing, we end up here. Can anyone see that? Right at the beginning of this string, right at the beginning. Now we need to go to the right. We need to somehow calculate here, tuk, 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 and then we need to store that here. So our R0 here, this one, points, as you remember with PC relative addressing, to the beginning of this string, right? And now we need to place it here.
Plus 7. So our store byte R0 R0 comma #7. This you read this notation as This is how the instruction means. Take the value of R2 and store it at R0 plus 7, indirect.
You need to remove now you have the null, because you've got another instruction.
Yeah, we added one instruction, so that's going to change the PC relative offset.
You have to remove the knob.
So we remove the knob because
Size, yeah.
yeah, we don't increase the length of the shellcode. We just add that instruction, remove the knob, and bam. If you're linking without the dash n, you'll get a segmentation fault. You need to definitely link with the dash uppercase n. Otherwise, the text segment is read only and the stub will fail. Yeah, the LD with dash n is important. Exec thumb works. And let's object dump it.
Yeah, beautiful. No null bytes.
No nulls. All gone. All nulls are gone. So does everybody have the shellcode? Ready? Quick walkthrough. This is the and then we're going to complete the exploit exercise. So this is your final shellcode. Few things to keep in mind. First is the arm to thumb switch. You branch to an odd numbered address. You switch to thumb mode. Then you have the R0 pointing to bin SHX in your literal pool. The store byte instruction will write a null at the end of your literal pool, so that now this byte is basically this is completely null byte free. Now typically, how do you then convert this assembly shellcode into hex code that you can cut and paste in an exploit? Typically, Metasploit will give you that stuff, so you want to now assemble a string. So here's how you go about generating the final shellcode. You assemble the shellcode, you link the shellcode as an RWX binary, then we use the object copy command, obj copy -o binary shellcode the ELF file, and then it will output a bin file. The bin file will only contain the raw bytes of the shellcode. Does everybody have the exact thumb working, denullified? So I'm going to now do object copy dash O binary exec thumb dot bin. This will just get the raw bytes into a bin file. If you just do an ls dash la, here you see this is a 28 byte shellcode. And now you can do a /hex encode .pl exec thumb .bin, and this is your ready to cut and paste shellcode. So this is how you go from assembling the shellcode, testing it, denullifying it, extracting the bin file, and then hexifying it. As a proof, let us check out whether it works in our exploit. Now here is the oops, I lost my shellcode. I'll dump it again and I'll copy the string. In your slides, at the end of your slide deck, I have the exact string set and all that. So that for your reference, you have it. But now let's look at this final exploit, smash1.pl. In smash1.pl, we have basically all the calculations for the offset and everything. That's all set. We also have a return to bxsp, and then it'll branch to the shellcode. Right now my shellcode is breakpoint, but we will replace this string $shellcode with the hex string that we generated. So simply paste the shellcode over here in the exploit in smash1.pl. And then we will save it. And now to test it, we will capture the output of smash1 in an environment variable. Just be very careful of the syntax. If you just do a /smash1, you'll see some junk over here. This output will capture into an environment variable and export it. So I'll say export attack. Choose a different variable if you guys want. Equals $bracket /smash1. So this will now save the output of smash1 into an environment variable called attack. if you do an echo dollar attack just to test, use it within quotes always. As a final test, let's run it with victim1 / victim1 into quotes dollar attack. And if you got it right, shell. That's your first shell. Questions?
Yeah, so this was a very simple shell. You can obviously make something more sophisticated, like a reverse shell. For that you need to figure out how would it look like in C, then translate it in assembly again. This will be a little bit larger, but same procedure. Right. You want to go into?
Yeah. So just to kind of wrap things up, the purpose of the workshop was to kind of give you an overview of the process of writing ARM assembly, shellcode, and testing it, pretty much the way we do it. That being said, in the world of ARM exploitation, there's very little work that's been actually done on shellcode. There are some publicly available shellcodes. The truth is they don't work. They only work on the author's QEMU. They don't really work on hardware. Now, ARM hardware is very different than Intel hardware in the sense that ARM follows a pseudo Harvard architecture. The data pipeline and the instruction pipeline are completely different. In Intel, these pipelines sync up. So Intel, you can have self-modifying shellcode. You can have polymorphic code. You can have encoded shellcode. You can have code that will decode itself. And then when you do the decoding, the instruction cache gets refreshed and your shellcode works. In ARM, you'll fall flat on your face. All the decoding will happen, but that will happen in the data pipeline. The I cache will not be synced up. Because who the hell wants to decode their own instructions? No one. Right? So when you try, a lot of people say, oh, you have ARM shellcode and SVC0 and then they encode it with XOR encoding and all that. It'll only work in QEMU. You try it on a Raspberry Pi, it'll flat out fail. That's why we always like to try shellcode on an actual hardware. And the thing is, you denullified yourself. One question though. Did we just not write back into our own shellcode? Did we not strb and write a null byte? Then how come it's working? And that too on hardware as well. It's a data. Literal pool is in the data, not in the instructions. So you can modify literal pools, but you cannot modify instructions. This is one thing about ARM shellcode that you got to remember. And lastly, I want to kind of give you an overview of how to go about writing your own reverse shell. So I'll just walk you through the last few slides. You all know the concept of reverse shells. What does a reverse shell do? Connect back. Why is it really cool? Because I mean, even the old concepts, like I believe this is the first documented paper on reverse shells. This is co-authored by me and my boss when we were working at Ernst & Young. And at that time, we thought about this whole inside-out concept. We called it an inside-out attack. We never really coined the word reverse shell. But the idea was that you exploit something and just get an exterm or a reverse telnet or native shell code come out on a back connection, and that goes through everything. Um, so the way reverse shell works is you need to have a listener, which is a green box. You run a letcat listener on port 4444. In the victim, what syscalls do you need to pull off a reverse shell? You first need to create a socket, then connect the socket to remote host and port. Then you need to redirect your standard in, standard out, standard error. So loop 2, 3 syscalls. And then lastly, you replace the victim binary by execing bin shell. The redirection is done already to the TCP socket. So that's how your reverse shell will work. Here is a snippet in C. This is how you'd write a reverse shell in C. You have to have the socket address data structure, which is always going to be 2 bytes of 0002. That is a TCP socket. The next 4 bytes are port number, and the next 2 bytes are port number. The next 4 bytes are IP address. Then you have socket connect loop 2 loop 2 loop 2. And exec v. This is somehow not shown, but it's appearing in white for some reason. But yeah, there is a socket FD call there. So if you want to implement your reverse shell, these are your syscall numbers. Syscall 281 for socket, 283 for connect, 63 for loop 2, and 11 for exec ve. Here is an approach. So you begin your shellcode with an arm thumb switch. You invoke a socket call, you write a null byte at AFINET address, you write another null byte at bin sh, then invoke connect loop 2 loop 2. We got to be very careful of the parameters. And this last slide shows you what parameters you need to place in each register. So for socket, the parameters are always going to be 2, 1, and 0, and it will return a socket descriptor in R0. This socket descriptor you have to reuse in connect and loop 2. So you have to save it in another register and then make the connect call. The pointer to the socket address will be in the literal pool. Then you do the loop 2s, and then lastly you do the exec VE. The exec VE bit you know how to do. So you want to take it as a nice exercise to work on. Write an arm reverse shell.
What did you say we get if we do it again?
You get a beer.
Pardon?
You get a beer.
Until
You get
tomorrow, so you
immense
have to
joy.
hurry tonight.
You do get immense joy, which is not doesn't compare to any number of beers I'll give you. Right. So, well, any last questions? Yeah, sure.
On the Pearl,
Okay.
we have BBBB as representing an address, right? Yeah, but should work.
Here we are. Yeah. This one.
Yeah. Why
This is not the program counter override. This goes into the frame pointer R11. I can easily just as well do this and 132. I just separated because when you return the function, your frame pointer gets overwritten and your program counter gets overwritten. I just did the BBBB to see the difference in the frame pointer. The actual offset to the program counter is 132. BBBB is not treated as an address at all.
Okay.
That's it. Right, well.
Well, if you have more questions about ARM assembly specifically, I guess Saumil showed it in the beginning of the slides. Desarialabs.com, you get all the basics. It gets a little bit more into detail. And there's also one tutorial covering specifically how to write this exec v shellcode that we just did, like step by step, in case you forget what we did and want to repeat a little bit. And yeah.
So yeah, let me put this up.
It's visible.
Yeah, so all the tutorials, I think it's back, it might not be visible.
So the issue is out there is you have 100
So tutorials on azarialabs.com. These are our Twitter IDs. Ladies and gentlemen, thank you very much for playing, even late at night.